There we go. Yeah, audio again. Cache. Engineering today. Why Ubuntu? It just works. It works, and it's what everything that I use is built on. So it doesn't really make sense to use any other distro. Otherwise, it's dependencies and fixing weird bugs for, distribution-specific stuff. I don't feel like doing that. Oh, I've got too many things open. There we go. Chad programming stream, Coggers. You know it, man. You absolutely know it. Listen, do you think we write single-threaded code here? Oh, that's disgusting. We write multi-threaded code. Storm blessed. Hey, it's nice to see you, buddy. We don't write single-threaded code here. This is a multi-threaded stream. This is a multi-threaded stream. That's just what we have to do. Listen, things are way too complicated now to not use something like multi-threading. We need a lot of performance, and we can't make transistors any smaller. Just making sure I have everything set up. I think we do. Do I VOD everything? Yeah. Well, at least everything that I did 6 months ago is on my YouTube. The stuff that I did Monday through Wednesday, I haven't exported yet. Same thing with the stuff today. But, well, I haven't done the stuff today. But I will export it all, and it'll all be on the YouTube, which I think is linked at the bottom. Hey Stormbless, it's nice to see you in both chats. But yeah, I'm going to be doing a lot more programming stuff. The compiler stuff and the programming language stuff, operating system, logic design. It was too hard. I was basically doing 5 books at one time, and it was way too complicated. So I'm sticking mainly to my area. So we're just going to do computer architecture and programming. My background, I'm not a computer scientist. I didn't get a degree in computer science. I got a degree in electrical engineering, and then I taught myself programming while I was doing electrical engineering, and I became a computer architect. So, we do our best. But I'm mainly self-taught in that respect. But GPU programming is very different. GPU programming is a lot more... you've got to have a lot better insight into the hardware, so it fits more naturally if you have a good hardware background, which is pretty good, because that's what I have. So what are we going to do? We need to talk a little bit about matrix multiplication today. So we already did the hello world of GPU programming. So we wrote this yesterday, a simple vector add kernel for the GPU. Very basic. We're doing it on 2 to the 20th elements. So, we wrote these 3 lines of code right here. And these 3 lines of code are doing an addition on 2 to the 20th elements. So it's doing, it's adding an array of size 2 to the 20A to an array of 2 to the 20B, and it's putting that sum into another array of 2 to the 20C. And we saw some of the basic things that we need for GPU programming last time that we need to understand, which is memory allocation. Very simple. We allocate memory on the device. We have 2 different things. We have, basically 2 different worlds, right? So on the one side, we have our CPU, and it's connected to its own memory down here. And then we have the GPU on this side, and the GPU has its own memory. Right? little bit different. Memory architectures usually vary. GPUs can have, or what GPUs tend to have is high bandwidth memory, or HBM. Usually computers like a CPU will just have DRAM. But that's main, so GPUs are very throughput and bandwidth oriented, so there's a reason why you want that different kind of memory. You really need something that's going to service, 100,000 threads versus something that will service, 16 maybe faster threads. So basically what happens is we allocate memory on the CPU up here. Then, so we'll just pretend these guys are connected over I/O, which they are. They connect over the PCIe bus, or in more complicated systems, they're connected over NVLink. NVLink's just faster, right? So this is, we'll just call this PCIe, right? So what happens, or I forgot what is it PCIe? No, that doesn't look right. I think it's capital PCI, right? PCIe, yeah. So it's PCI Express. So basically what happens is we allocate memory. So we say, all right, we need this memory on the CPU. Then we do CUDA malloc, and we say we need this memory on the GPU. Then we initiate a transfer. So we say, okay, I need this memory to go to the GPU and eventually get into GPU memory. That's the basic idea of what we're doing. And so that's what this allocation, this CUDA malloc is allocating memory. This CUDA mem copy down here is actually doing this copy. So it goes through this copy engine system. It goes through the L2 cache. So when we're doing a mem copy, we actually, the mem copy, it actually goes through the L2 cache first. So even if your program doesn't have a ton of locality or something, you basically do a little bit of prefetching at the very beginning because you basically fill your L2 cache with whatever you copied in. And so it's really good if you're copying a small amount of memory, you'll basically fill up your L2 cache. Chat overload we got here. We're going to have a good stream today. We got some nice coffee. We've got some nice programming stuff set up. We'll have some fun. So this is our basic system. We talked a lot about the basic details of doing a basic CUDA program last time. I know I said basic a lot there. These streams usually begin when I've had about 3 beers already, though. Listen, this is, considering I don't have a PC at home, this is the best time that I can do right now, especially since nobody's in the lab right now. Usually I had to do these later about 6 months ago because there's people in the lab until like 6, 7 p.m. But it's only 5 p.m. here right now. All right, so what are we doing today? I wrote a compute shader once and nearly collapsed with the stream. Well, hopefully this will be a lot different because, depending on what you wrote it in. If you wrote it in CUDA, depending on what you were writing, I mean, CUDA is fairly simple, but all the difficulty in GPU programming comes from OpenGL. Okay, well, I've never written OpenGL. I can say, though, that CUDA is very, very friendly when it comes to writing compute stuff. Back in the day, they used to have to map textures to, or they'd have to map problems to texture. So if you wanted to do matrix multiplication, you had to map it as a texture and then, do some crazy stuff dealing with textures and then get out the result the other side. But now you can just write a matrix multiplication kernel, which is pretty nice. All right, so let's see. Let's talk a little bit about matrix multiplication. So what do we need? We need a new page. Right? So first we'll exit out of this. And we'll make a new file. Oops. basic matrix multiplication. Now, if you want to be technically correct, it's matrix multiplication, but, you know, everyone calls it matrix multiplication. And new page after. So what are we actually doing here? So let's zoom in a little bit. So let's start out with the very basic. So what is matrix multiplication? Matrix multiplication says we have two matrices. We're multiplying them together, and we get some output matrix, right? Now, how does this look in reality? So in reality, if we want to look at this more in terms of what does it look like as far as mapping a problem, we'll call this matrix M. We'll have matrix N, and then we'll have our product matrix right here. Now, for sake of simplicity, we'll do this with, we'll just call this P. For the sake of simplicity, we'll just consider square matrices, because square matrices are easy to work with, and when it comes to doing things like scaling the number of threads we want, it's really convenient if they're a power of 2, just because the number of threads per warp on Nvidia GPUs is 32, so that's a power of 2. So, you know, we like things that are powers of 2. So we'll just consider square matrices for these cases. The only thing that changes if you don't have square matrices is you have to add a little bit of padding and make sure that you don't go out of bounds. But, you know, how do we actually calculate any of these elements? So it's fairly simple. So if we consider these to be, say, 2 by 2, we end up with a 2 by 2 matrix as a result. So a 2 by 2 matrix. So a 2 by 2 matrix times a 2 by 2 matrix. Little trick is you always, you know, that's going to be the size of your product until you end up with a 2 by 2 matrix. Now, each of these individual elements in these 4 locations will end up being a sum of products, right? Yeah, it's a sum of products. So if we take a very simple example, right? So if we take a matrix 1, 2, 3, 4 times a matrix, let's see, 4, 5, 6, 7, right? Let's just do ascending order just for, you know, just for fun. So if we put this in that same form that we had up there, so we'll have 1, 2, 3, 4. Up here we'll have 4, 5, 6, 7. And this will be our product down here. Now, remember, we're going across and we're going down, so this will be 1 times 4 plus 2 times 6. This will be 1 times 5 plus 2 times 7. This will be down here 3 times 4 plus 4 times 6, and then this will be what? It'll be 3 times 5 plus 4 times 7. Right? Something like that. So, pretty simple. Now, there's some very obvious ways that you can make something like this parallel. Let's go through just a couple of them for fun. So, what's way number 1? So way number 1 is we're going to take a matrix like this. Well, I guess we should first say how would we do it serially. So to do it serially, we would do exactly what we just did. We would go, okay, let's just do this all in a couple of for loops. So first we'd go, okay, we have to do every single row in a matrix. So we'd iterate over all the rows. Then for every single row, we'd have to go across and touch every single element. And then we'd also have to touch every single column. So we'd need to go, okay, so I need to do 1, look up 4, multiply it. And then I'd need to do another loop, and then I would have to go over 1 and do okay, 2, look up 6, multiply them, add them together. So it'd be a lot of these partial sums. Eventually, at the end of an entire set of loops, you will have done all your computation. So let's think about how we'd make this parallel. So the very obvious way to make it parallel, which is a way that we're not going to be doing, but just as a fun exercise to think about. So if we had this same problem set up, we could just assign a thread to every single row, right? Pretty simple. We just pack a bunch of work into all these threads, but now instead of doing all these threads at one after another, or doing all these rows and multiplications one after another, this time we can just launch as many threads as we have rows, and we got a decent amount of parallelization there. It's not perfect, it's not great, but we got a decent amount of parallel work going on. Now let's be a little bit smarter about this. So we can actually do a little bit better. Well, we can do a lot better, but let's just take a look at doing a little bit better. So if we have this same type of problem where we have all of these different matrices up here, right? How about instead of having, a thread per row, let's do a little bit cleaner, and let's have, for every single element in here, so let that be a row of this particular matrix, and then let this be a column of this particular matrix. So this will be N, this will be M, and this will be our result or our product. Now, we'll just be focusing on this single element, and so we'll assign every element a single thread, and that way, when we get to the actual computation, all it has to do is iterate over this row and this single column, and we get this small result right there. So if we just kind of extend this down a little bit, that's the work that we're going to pack into every single thread. Right? Nothing too terribly complicated, but we see that we squeeze a lot more parallelism out, right? So so if we had n rows before, and we did the simple method, we'd improve how much parallel work we're doing by n. But now that we're doing it now for each element instead of just each row, now we're getting n squared parallelism here. So for every single element, there's going to be a single thread. All right, any questions on any of this so far? Should be fairly simple. We haven't done anything, we haven't introduced anything terribly new so far. But this is a very naive version of matrix multiply. There's more advanced things that we'll cover maybe tomorrow or maybe sometime later that involve doing something called tiling. And what we do when we tile things is we say, hey, I have a lot of locality in specific regions. I want to make sure that I keep that data around in very easy to access data structures or physical memory structures for that period of time. And so in order to do that, you tile a problem which says I'm only going to work on these small tiles, but these small tiles will all access the same or mostly the same data. But for here, we're not going to care about that. For here, all we're going to do is say, okay, we're just going to pack a bunch of work into single threads. So we can go ahead and start writing. Engineering Today, can you enable PepOG in your chat so I can take notes? I would if I knew how. I'm afraid I don't know much about Twitch management or extensions or whatever that requires. So let's go ahead and continue. So we can go ahead and open up vector add side by side. Let me move the drawing tablet a little bit out of the way so I've got some room to type. So everything starts the same. We'll all start with a main function. Then let's see. So we should specify a problem size, right? So let's say we want to multiply two 1024 by 1024 matrices together. It's a fairly large size, should give us a decent computation to work with. So we'll just say size n is equal to 1024. So 2 to the 10 is equal to 1024. So this is equivalent to 1024. There you go. This is just a cheating way if you want to scale something up really quickly, right? You just do arithmetic shift. Because when you're talking about arithmetic shift, or it's talking about shifting bits, and so bits are base 2 because they can only be 0 or 1, so you'll multiply it by 2 every time you shift it over. Okay. So what do we need? We're going to need a couple matrices. So we're going to need a matrix M and a matrix N. So first we'll have an int. We'll call this, we'll do an int pointer because we're going to have an array. So this will be host M. We'll have an int pointer, and this will be host, host N. And then we'll have another, a final one, which will be our host product. This we'll copy back our results into. Right? So this will be our host matrix. And then on the flip side of it, we're going to also need to allocate some space on the device. The device being the GPU. So let's go ahead and just do the same thing. So we'll just copy these, right? And so this will just be device. And we'll just change the prefix to D. Very common thing if you're looking at GPU code, if you see H or D as a prefix to something, that generally means host and device, or CPU and GPU. Okay, so what do we need now? Exactly like we did. Well, let's go ahead and include some. Let's include some stuff first, just for convenience, right? Well, we're going to need it anyway. So we need to include sto.h if we want to print out some stuff, and we also should include the standard library. Why do we need that? We need malloc to allocate. We also need rand if we want to randomize the input to the matrix. Okay, so what comes next? Next, just like up here, let's go ahead and calculate a convenient, how big are these matrices, like how much actual physical memory are they going to take up? How many bytes of physical memory, I should say. So in this case, we'll call it the exact same thing, bytes, except this time it will be n times size of int. Now the reason why it's n times n is because it's a matrix, so it's not just a vector of n elements, it's a matrix of n times n elements. And then it's going to be a matrix of integers, so size of int. So that'll give us an int on pretty much every system is 4 bytes, so this will be 4 bytes times n, so it'll be 1024 times 1024 times 4. Okay. So let's allocate our host side. Allocate memory on host side. We can go ahead and move down a little bit. So, exact same thing we did up here. In fact, let's just copy the code. We'll copy the code, and we'll change it a little bit because we called this M and N and P. And then we can, let's see, I think that's all we need to do for that. And then we should go ahead and initialize these as well. Initialize matrix M and N and P. Yeah. Any question on anything so far, CUDA related or just general programming related? Now is a perfect time to get your questions answered. I listen in, and I float, oops, in. Some of the highlighting's messed up in my vimrc file. I was trying to get all the CUDA highlighting in here, so it would highlight things like CUDA malloc and all those functions, but something happened when I updated it, and now I get weird bracket highlighting and semicolon highlighting within loops. I need to take a look at that sometime. All right. So what we need to do, so this is a matrix, so we need to allocate both sides. So we need another for loop in here because we need to, for every row we need to allocate, and then for every column we need that individual element, right? So we'll just call this j for int j equal, oops, j is less than n because we're assuming it's a square matrix. And then we'll just do j++. Okay. Make sure we close that out. And then now we can go ahead and just start initializing. So we'll do h of m of I of the ith row and the jth column will be equal to rand and then mod 1024. We'll just say that it's some number between 0 and 1023. There's no real specific reason why it has to be like this. This is just random initialization. Right? And in should be the same. And for convenience, we can just do return 0. Right? Let's see. Let's see if I made any mistakes so far. There's an easy way to check, and that's to compile it. So this is matrix mul. We'll call this matrix mul.out, and then our input will be matrix mul. Oops, it's not installed. I didn't source the correct file. Let me just move this over and I'll source it. All right, there we go. Source now. Let's run that again. All right. Expression must have pointer to object type 29 and 30. And a bunch of warnings for declared but never used. So let's see what we messed up. Matrix mul 29 and 30. Right? Did we not do this right? Yeah, we'll just do this all in one, right? So we'll just do I times n plus, what's it going to be? I times n plus j, yeah. Let's see, I think I messed up something. Let's make sure. So we're just doing a scaled, so because all of this is in row major order, which just means we're looking at it like a matrix, but when you look at it as in terms of an address space, it just looks like sequential addresses. All right, there we go. Okay, so we fixed it. Yeah, I forgot, I initialized it just as a linear array. I think it doesn't like it if you do that and then you try to index it like you initialize it as a multi-dimensional array. So all we get now is a bunch of warnings about variables that are assigned but never used. But it compiled successfully. And if we run it, it shouldn't segfault or anything. It basically just, there's nothing going on right now. We're just initializing matrices. But it's always good to compile your code. So now we have two 1024 by 1024 matrices that have been successfully allocated and initialized. So now we need to do the GPU side of things. So let's start allocating memory on the GPU side. So just like we did before in vector add, we'll do the same thing. So we'll just call CUDA malloc. Right. And we can even borrow this code. So remember, we changed these names to DM, DN, and DP, I think, the product. Let me make sure. Yep, host product and device product. So all we're doing here is we're allocating bytes, which is the size of a matrix, a 1024 by 1024 matrix of integers to be specific. And we're just allocating these in the device. Okay, so that's about all we can do before we start writing the actual GPU kernel. So far, what have we done? All we've done is allocate data, and we talked a little bit about how we're going to proceed as far as every single thread that we launch is going to compute a single element of this product, right? So let's actually see what we need to do next. So what is our kernel going to look like? So the first thing we should always think is, how am I going to index these threads? How is each thread going to know who it is? So because we're doing things that are two-dimensional, so we have these two-dimensional matrices instead of one-dimensional vectors. If we look back up to the top of the vector add kernel, we see that we're still just using this big long line of threads. So everything is just some linear combination, some displacement, right? So it's the block ID x times the dimensions of the block plus the thread index of that block. That's just going to be the equivalent of, here's my, I don't like that. It was being nice to me yesterday by correcting that to be, there we go. So if we have all these threads, and let's just say this is an arbitrary boundary, right? And let's say that these are two different thread blocks. So this is thread block 0 and this is thread block 1. So what are the block ID, block dim, and thread ID x going to look like for each thread here? So let's just take one at random. So let's take this guy. So globally, this will be thread 5, right? The indexing for threads start at 1 because that's what they decided. They didn't. It's mainly for computational purposes. Things get a little messy if it was 0. So I think they start them at 1. Thread blocks, though, start at 0, but threads start at 1. So if we want to index this, how does this align with this formula that we did earlier? So remember, this is just some linear array of threads that we're looking at for this one-dimensional problem. So it will be, our block ID will be 1. Our block dim, there is 3 threads per block. And then what's the offset within that block? So this is going to be, or maybe they do start at 0. I think they actually do start at 0. I think the sizing starts at 1, yeah. So, and then it's going to be the second thread within this block, right? And so the block or the thread ID here will be 0 and then 1, right? So this will be a total of 5, right? And that's for this guy right here. Pretty simple. Now, this works fine if we have big long vectors because, all we really care about is these. All we really care about is one dimension anyway, because we only have a vector that grows in one dimension. But if we have a matrix is going to expand in multiple dimensions. So this same idea of just using some global thread ID doesn't really make sense, especially if we're mapping every thread to a specific element that has you can think of it as an x and a y coordinate. So are you allowed to use assert in vector add? Yeah, I think you should. Well, you can. I mean, are you saying in vector add as far as the? I'm guessing you mean inside the actual CUDA function itself. I think you can. I think it's supported in CUDA. But you really don't want to do that. I mean, you'd rather just assert on the host side. So you want to check to make sure pointers aren't null and you have proper sizing for your problem before you launch it on a GPU. You generally don't. It's generally more of a look before you leap kind of methodology, not a easier to ask forgiveness and permission. Like I think you can use asserts within GPU kernels themselves because it basically supports most of the C and C++ standard. So asserts are going to work, but yeah, better to just check ahead of time. Which is, if you look at any kind of production code, what production code will do will, before it launches on the GPU, especially something like matrix mul, it will say, okay, are the dimensions of the matrices, is this a valid matrix multiplication? And then also a lot of times, there's no real reason why you would ever have a null matrix, right? Or a null pointer. I mean, that's more like a debugging kind of point when you're writing this for the first time. After it's written, it should just work, right? All right, so let's move on. So we talked a little bit about this 1D indexing, but we need something a little bit stronger now, so we need to start looking at multidimensional indexing. And so that's one of the convenient things about CUDA, is that they provide threads, but they provide it in an abstraction where you can think about it in 2D and even 3D. We're not going to use 3D most of the time, because most of the problems that at least I solve, or most problems that people solve, they solve it in 2D anyway, because people think a lot better in 2D than 3D anyway. It's kind of like parallelism. People don't think well in parallel, they think well serially on a problem, which is why most code that you see is serial in nature. And once you get to parallel code, it becomes very hard to reason about. All right. So let's switch back. So let's go back to this problem. So let's say that this is our matrix that we're working on. Now, let's say that each one of these elements in here represents a thread. So in this case, we can just have, let's just call this our thread block for simplicity. We'll use a slightly larger version. We'll use a 16 by 16 to solve our problem. But in this case, let's just use a very simple 4 by 4, just because we're doing this on paper. And I'm not going to draw 256 small little threads, right? So if this is our thread block, let's see how we're going to get each of our individual thread. Let's see how we're going to find this value. So originally our thread ID was just going to be, some linear offset. But now we need to play it a little bit smarter. We need to calculate two things now. We need to calculate a row and we need to calculate a column. But neither one of these things is particularly complicated. So this is going to act exactly like every other XY grid you've ever seen before in your life. So if we think of this as the x-axis and we think of this as the y-axis, the built-in variables that allowed us to do block ID x.x, block dim.x, and then thread ID x.x, it turns out there's a .y. It turns out there's a .z if we really needed it. So if we want to find this guy's row and column, that's exactly what we're going to do. So if we want we can go ahead and switch back to programming, just so I don't have to write code by hand. So let's go ahead and make a matrix multiplication function up here. So remember, CUDA functions or GPU code, it's going to start with a prefix global. It'll be void. And then we'll call this matrix mul. And then we can go ahead and put m matrix n, and then our product matrix P, and then our size N. Right? Very similar inputs. So what we're going to do first, we want our row and column. So if we want our row is going to be simply very similar like it was before. This time it'll be .y times block dim.y plus thread idx.y, right? So let's see why that is. So we're assuming that we have these square thread blocks now that are 4 by 4. So what does this mean for this guy? So our block ID x, this is a single thread block so far, so it's going to be 0, so this entire term is going to be 0. Now our thread ID x.y just says, okay, where is this guy going to be? This guy is going to be in the 0th position in the y-axis, right? So that's assuming that, we're growing downwards and we're growing to the right. All right, that's typically how you can think about this, although you can think about it the reverse way, but when you're thinking of a matrix, a lot of time you think from top left to bottom right, just kind of like you're reading a book. And that's how all this indexing works. And so we'll just call this row. Thought I wrote out row. Right. And then we'll have column, and this is just going to look exactly like our regular thread ID calculation. So we can run through a couple examples of how this is going to work. So for something like this guy right here, its x position is going to be, if we assume that this is 0, 1, 2, 3, and this is 0, 1, 2, 3. If we look up this guy right here, it's going to be at 0, 0 for that first thread. And we can do this for any arbitrary one, right? So for this guy right here, he'll be at 2, or sorry, 2, 2. Right? And so if we scale this up and we start adding more thread blocks, the only thing that happens is we just get scaled on both sides, right? So our block ID X and our block ID Y is going to change. So if we move 1 over to the right, we're going to get a block ID X increased by 1. If we move down 1 or something, we'll get a block ID Y added to 1. And then the dimensions of Y and X, for this example, they'll be 4 constant. We don't have changing block sizes within a single kernel. You can have multiple kernels. You can have multiple kernels running concurrently with different block sizes and different dimensions, but for a single kernel, they all have the same block size. At launch time. You can launch them with different parameters, but at launch time, they'll all have the same. Which makes sense because you're generally scaling problems up. You'll scale a problem, you're scaling the same problem, so generally if you wanted to change block size somewhere in between, all of your code inside your actual program, your algorithm is usually tailored to certain dimensions of your launch parameters. So that's why it's typically constant. Well, not typically, it's always constant. All right, so that's our row and that's our column. So we've got most of matrix multiply honestly done at this point. What do we still need to do? So now we just need to, for every row and for every column, all we have to do is make sure that we're doing the right computation for that specific element. So just like a matrix multiplication that would be sequential that you would do on a CPU, it's going to require a for loop. So int I equals 0, and then we'll iterate over the entire length, right? So because these are square matrices, we're iterating over the same length on both sides, so it makes things pretty easy because we just need to go over an entire row and an entire column, both of which are the same. So the same length, that is, not the same elements. So we'll do int I equals 0, I is less than n, that we'll pass in later. We'll pass in 1024 in our case, and then I plus plus. All right, so that's our iteration. And we'll also add up here for every single thread, because it's doing a single element of computation, we'll add a partial sum element up here. Right? The reason why we need this partial sum element is because at every step it's going to be multiplying two things together, and we need to add all those up. Remember, it's matrix multiplication, something that we've done many, many times in the past. It's a sum of all of these little products. All right. So what do we need to do here? So like we said, it's some basic sum of products. And now we just need to do find the correct place inside of our row and find the correct place inside of our column, right? So for a row, we're just going linearly across. So we need to make sure we're on the correct row. And so in order to do that, we'll take our matrix M. That's just like normal matrix multiplication. If we're doing M by N, we want to stride over these M element, or this row of elements on the M matrix and this column of elements in the N matrix. So how do we index that? So it will be our row times in. That's going to give us the correct row, because remember, when this gets placed out in memory, it's just going to be a linear, it's going to be in row major order, so all of these things will get put in a big long line. So you'll have the first row of the matrix will be elements, say, 0 through 4, or 0 through 3. Then the second row will be elements 4 through 7. But they'll all look in a straight line in physical, or not in physical memory, but in the virtual memory abstraction that you're given. And then we just need to add I to this. Right? It's going to be plus equals. And then we need to multiply it by the correct column. So that's going to be our in matrix. So in this case, we want our, let's see, so if this is going to be striding over the different rows, this one we want basically it to be kind of reversed. We want it to be the column no, it's going to be I times n plus c. Does that make sense? Let's see what that's going to give us. So it'll say we're going to go over every single column. So we have n columns. We're going to go through every single one, and then the offset within that column is going to be c. I think that's going to work out correctly. So yeah, because it's going to be, let's just work it out on paper real quick, make sure. So let's see. So this guy right here, remember these are all going to get, so if we have a 4x4 matrix like this, these will all get linearly put into memory like this. Can I move over anymore? No. Right, so these will all have 4 elements. All right, and this will be our 1, 2, 3, 4, our boundaries, right? So this will be row 0, row 1, row 2, and then row 3. So when we're accessing the different columns, it's going to be, so for the first one, for the first one we're going linearly over. So it's going to be this, then this, then this, then this. So we want the row times n to get the specific one. So in this case it will be 4 times what row we're on. So if we're on the 0th row, row would be 0, and then it would be plus I, and then I would be from 0 to 3 in this case. So that works out. Now if we want to do the different columns, let's say we want this guy, then we want this guy. It's going to be strided, right? Because when these get placed out in memory, it's still going to be like this. So if we have a matrix like this, and we want this right here, each of these rows will be linear put into memory. So what we need, we need for every single, we need to iterate over all of these rows. So the rows will be from 0 to n, which will be our I right here. We need the displacement times n, and then we need the individual column, which should remain the same all the time, right? So in this case, if we wanted this guy, it would be the 0th, so it would be 0, times 4 plus 0. And then for this guy, it would be 1 times 4 plus 0. And then for this guy, it would be 2 times 4 plus 0. So yeah, looks like we got it. All right. So that all does our partial sums. Sometimes when you're doing these index offset things, it can get a little bit confusing, especially when you're doing when you're not just straight indexing it like a matrix, when you're actually doing the offsets. Column times I plus n, or no? Yeah, I times n plus column seems right, yeah. Okay, so let's see. So what else we have? Okay, we need to put it in our final matrix, our product matrix. So now we need to index into our product matrix. We need the right row. So it will be our row times n plus column will be equal to our partial sum. And so this is because we directly know exactly what element we're computing. We're computing this row and this column. And we just need to do a little bit of scaling because remember, this thing gets laid out linearly in memory like this. And because it gets laid out linearly, we have to do this offset. And this offset is just going to be the size of each row. So fairly simple, but it's just this linear displacement we need to remember. And yeah, I think that's pretty much everything as far as this is our kernel. We're done with our kernel now. This is square matrix multiplication. If we wanted to make it a little bit more robust, we'd what would we do? We would make sure that it can handle thread blocks that might have threads that aren't doing useful work, so we'd add a couple boundary checks in there, but because we know we're giving it square matrices, we can play it a little bit dangerous right now. Okay. So let's get into what we still need to do. So all we've done so far is we've allocated data. Oops. Let me get rid of the highlighting for a second. It's a little bit annoying. All right. So the next step after we've allocated data is we need to start copying over data. So in order to copy over data, what we do, exact same thing we did on vector add, is we're going to do some mem copies. So this will just be copy data to the device. So we want to do the device M from the host M matrix, and we want bytes size, and then over here we're copying over N to the, or copying into the device N matrix from the host N matrix, both things we initialized here. And yeah, that's what we have. Then eventually we can be a little bit presumptuous and we can go ahead and write our copy back statement. So we can do our device to host, and this will be from device P to, or sorry, from, we're copying into the host pointer from the device pointer to the product matrix. So all we have left is to actually call matrix multiplication, right? So we need to call matrix mul. Now we still need to do our thread block and thread ID, or sorry, our thread block and grid size calculations, but we'll do that next. We'll just go ahead and set everything up. So here we need, I believe it was, we did it in order dm, dn, and dp, and then this will be the size of the matrix N that we'll pass in. Now, yeah, the only thing left that we have to do is do our block size and our grid size calculations. So how do we do that? So the first thing that we'll do is we'll set a thread block size, and this will just be for convenience. It's often something that is it's a tunable parameter, which means that there is no right answer. There's a right answer depending on the problem you're solving. In our case, we'll go with something very simple. We'll do a thread block size that's 16 by 16. It's a very easy way to cut up the problem, and it's a square. So it fits our problem type of multiplying square matrices together. So we'll just say int max threads, or we'll say int threads is equal to 16, or we'll call this threads per block. It's probably a cleaner name to put that. So we'll do a dim3, which is a parameter type that's in, it's a CUDA specific parameter type. They're basically these three-dimensional XYZ structs that you use to, they're convenient ways to do launch parameters, so you put them in a dim3. So we'll do a dim3 block size is equal to threads per block, comma, threads per block. I think this is how you initialize these. I don't write these very often. And then we also need a grid size. So this will be how many blocks in each direction we need to initialize. So remember, when we're doing matrix multiplication like this, let's get a new page. If we're doing a, ooh, that was very off. When we're doing a matrix multiplication like this, what tends to happen is we'll now this isn't tiling, but it's very much like it. We'll have our matrix, and our matrix will end up being composed of our 16 by 16 blocks like this, right? So it ends up being, you know, 16 by 4 this way, and maybe 16 by 4 this way. So it'll be a integer multiple, because we're doing these square matrices that are multiples of base 2. So that's what each of these thread blocks is going to represent. So if we actually want to do the size now, all we need to do is over here is n divided by block size.x, and then n divided by block size.y. The .x and .y, that's just a function of, that's just a method that's built into that dim3 data type. That dim3 data type has .x, .y, .z, and they're initialized in order. So if you just wanted one, like a linear thing, so you just use .x, you can just throw an int in there and it works. Let's see. So all of this should compile now, besides matrix mul, because we haven't put anything in there. So let's just comment this out, make sure we don't have any silly mistakes. Let's see. Duplicate parameter name. Oh, we do have some silly mistakes. So let's see. So let's go to line 6. Int mpn. Oh, sorry. So we'll just call this size instead. Sometimes you wind up doing silly things like that when you use very simple names. That should fix that one. All right, C is undefined, so let's fix that. Let's see. Oh, yeah, because we call it column, not C. Anything else? Nope. There we go. Expression has no effect, but that's because we're not doing anything. All right. So, no more silly syntax errors, which is good. So, now we get to actually flex our muscles a little bit and start launching something. So remember, these triple chevron notation, triple bracket notation, depends on who you're asking, is what they call it. So the first parameter is going to be our, I think it's grid size. Yeah, we can check up here because I did it correctly up here. There we go. Yeah, it's our grid size. So that's going to be the size in the x direction of how many blocks in the x direction, how many blocks in the y direction, which is what we said here. So we can just pass this dim3 structure in, so grid size, and then our block size is just going to be how many threads in the x direction and how many threads in the y direction, y and x per block. So that'll be our block size. Now there's two more ghost parameters here that will just be 0 for now, and they're implicit if you don't specify them, and that's going to be the amount of shared memory and the streams, which stream you're putting it on. Shared memory only matters if you're specifically managing shared memory on your own, which we'll do in the next stream. So we'll do a shared memory tiled version of matrix multiplication. And then the stream size only matters, or the stream number only matters if you're doing concurrent tasks. So if you're doing multiple kernel launches and you want them to happen in parallel, not sequentially, then you would do it at multiple different streams. But we're doing neither of those things, so we can leave them out. Okay. Let's just see here. Make sure, oops, did I write everything? Yeah, everything's saved. Make sure it compiles, oops, at 62. Ah, we didn't do a semicolon. Silly us. Oops, I didn't write a makefile for this. All right, so what happens? 57, 58, 57, 58. What are 57 and 58? Dim3 has no effect. Let me make sure that I have this correct, right? CUDA dim3 initialization. Oops. Okay. Yeah, right. It's just a constructor, so I don't need to specify like an equals. There we go. All right. I think that's what it's saying I can do. There we go. All right. No more errors. That's what we'd like to see. It's easy to make simple mistakes like that. Time to time. All right. So that's our kernel. We'll go ahead and do, we'll look at the assembly real quick using CUDA object dump dash sas for matrix mul.out. Right, and we'll move it back a little bit. So this is our, this is the code for matrix multiply. As you can see, it's significantly larger than the code that we had for vector addition. But we see a couple common things. We see that we still have these built-in variables that we can access from the ISA level, the instruction set architecture. So we see that CTA ID, so our thread block ID. A lot of times thread blocks are called CTAs, or cooperative thread arrays. Two names for the same thing. So there's a cooperative thread array, CTA ID Y, thread ID Y, CTA ID X, thread ID X. So from what it looks like to me, this is a lot of work to calculate our row, and then this is not a lot of work, but this is our work to calculate our column, right? And then we get down into all these conditionals and nasty adds and moves. This is all things that's going to relate to the loops and loading stuff in from memory, all things that we don't really need to worry about too much. We'll usually see a lot of these ISC adds. This stands for integer scaled add, so just so you can see it. Where'd it go? Where is an integer scale add? There we go. So here's like an integer scaled add. This is used a lot of times for those index offset calculations. Basically because all it does is it says, okay, take whatever your, so you're going to do an addition, but you're doing a scaled addition. So you'll take some number, you'll scale it by another, and then you'll add a third number. And then, but you're scaling it by an integer, so it's not like a floating point. So you don't use like a floating point unit, you'll just use the normal ALU. So yeah, so we did it. Okay. There's our matrix mole. We can just run it and see if it crashes. Okay, so it doesn't crash. It's pretty useless right now because we don't have anything testing correctness on it. But that's matrix multiplication for you. So let's go back into our code. Right. Are there any questions before we continue on and do a couple more things? Any GPU specific related questions or CUDA related questions? Or architecture related questions. See, I mainly do computer architecture. I do this programming kind of on the side. But it's necessary. You need to know what software is being written in order to design hardware. Okay, so what we should probably do for verification. Well, first of all, let's just print out some sanity things. So what do we need? What should we print out? So we should print out let's do grid size X. Oops. And this will be %D. And then grid size Y. And this one, another %D. New line. And then we'll do block size.x. And then block size.y. Yeah. So this is just, we want to make sure that our problem is being split up correctly. All right, so it's being split up into a 16 by 16 total grid. So that means we have 256 total blocks. We have 256 total blocks times. Yeah, that makes sense. So why is that so? That's because we have square matrix of size %d, and this will be in right. Yeah. Okay, yeah, there we go. So yeah, so we're splitting up this 1024 matrix, and we're computing all of this using a 16 by 16 grid of 16 by 16 thread blocks. Let's see, what else should we print out? So we have, yeah, threads per block here. What are we doing here? In divided by threads per block. So, oh, sorry. What am I doing? Oh, I'm printing out the wrong thing. Yeah, I was wondering why that didn't make sense. This should be grid size. I don't know why I put block size. You guys got to catch me on this. I was wondering because it wasn't lining up to 1024 by 1024 elements total when I was doing the calculations in my head. There we go. So this should be correct. Yeah, 64 by 64. So the reason why this is correct is because if we have a 64 by 64 grid of 16 by 16 blocks, that means it should be 64 times 16 times 64 times 16. All right. Now, who knows the fastest way to make sure that this is going to multiply 2 to the 10 things together? So it'll be a 2 to the 10 by 2 to the 10. I'll give you a hint, there's a really easy way. And the really easy way is by noticing that these are all powers of 2. So this is 2 to the 6 times 2 to the 4 times 2 to the 6 times 2 to the 4. Right? So when you multiply exponents together, you can just add them if they're of the same base. So this will be 2 to the 10 times 2 to the 10. All right. You said the scaled add opcode uses an ALU. GPU cores aren't microcoded, are they? My grasp of GPU architecture isn't great. You said the scaled add opcode uses an ALU. GPU cores aren't microcoded, are they? So if we can actually just look at the architecture that Nvidia gives us if you want to know more about it. So let's just go to it. Volta architecture white paper. That's a great thing. If you just look up these white papers, you can learn so much about GPU architecture, CPU architecture even. So this is kind of a high-level view of what a GPU is going to look like. But the actual SMs that you're running things on, they have a better picture down here. So they have these integer units in here. So they have integer units and they have floating point units. Right? And so when we did that object dump, the CUDA object dump earlier, that gives you the low-level SAS instructions. So SAS stands for source and assembly. It's the proprietary instruction set of Nvidia. They release another one, the virtual instruction set called PTX. But yeah, that's what the and there's these tensor cores over here that nobody uses but Nvidia, because they're the only ones that can program them. Not literally they're the only ones, but they're the only ones that put in the effort to program them. They're not very user-friendly, besides through like the libraries. But yeah, so there's all these floating point units per SM. So this entire thing is an SM, and they have these individual they have these individual little parts to it so that they can split up and they can divide a lot of this work. And so each one of these things will have a warp scheduler. So these are groups of cores with shared memory. Yeah, so you got to be careful when you... I can just look at that. Didn't mean to derail. Oh no, it's fine. We're pretty much done with matrix multiplication. We wrote it. We kind of checked it. We'll write a quick sequential version of matrix multiplication in a second, just to verify our output. But actually, let's just run it with the profiler real quick. So we'll run it with Nvidia's Profiler, NVProf. Let's see how long it takes. Decent amount of time. So we're doing a 1024 by 1024 matrix multiplication that we've tiled out into, we've packed work into these threads and we've split it up to be parallelized on a bunch of the different cores. So let's see, are we using every single core? Well, core. Cores mean very different things in GPUs. Like, so what's a core on a GPU? Is a core an SM? Is a core an individual one of these units on an SM? It's hard to say. But SMs themselves have a couple very specific things. So they'll have so there'll be an L1 data cache, and then there'll be this local shared memory. And this shared memory, which we'll do next time, is typically used as an optimization. And the reason why is because a common CPU optimization is cache tiling. And it's where you basically kind of figure out how big of a footprint your data is, and you look up the parameters of your CPU and you figure out, okay, how big is my cache? And then you make sure that your data will fit into that cache. Now, it's very different in GPUs because GPUs just tell you how big everything is. And specifically with shared memory, so 96K of this 120K data cache can be shared memory. So you basically have 96K per SM of a programmer managed L1 cache. And so what do you do with this? So if you know exactly what your program is, well, you should know exactly what your program is doing. But if you're smart enough to go, hey, I know what data I should be keeping around better than a hardware managed L1 cache, you can say, okay, I will explicitly load things into shared memory that I know I will reuse. And yeah, you can boost performance that way. And a lot of times you get a way better scaling with an optimized shared memory version versus some generic managed version. But there's other optimizations that go in there as well, because you're not just doing the same, you're not doing the same program plus shared memory. You're generally changing your algorithm so that it's, it's tiled or something instead of just, calculating a single element. You'll calculate a group of elements in a cluster. So basically like this picture we have, here of our different thread blocks, the way this generally works out is suddenly instead of it being thread blocks, you'll have tiles in here, right? And so each of these tiles will reuse a lot of the same data. Hey, Engineering Day, came by to say hello. Well, hey, Versuch, it's nice to see you today. We've been doing some GPU programming. Let's see what time it is if I want to spend time on doing a sequential version of matrix multiplication. Void matrix mul int. So this will be matrix mul sequential. Let's see how quickly we can get this done. I'm busy right now, but I'm glad to see you streaming again. Well, hey, it's nice to see you. I hope you're not too busy. It's a new semester. Everyone's having fun. I figured I'd stream about 1.5 hours a day. So I'm almost done as well. I'll be done a little past 6:30 probably. All right. So we'll use the exact same kind of inputs. So we'll have a matrix M. We'll have a matrix N. We'll have a product matrix, and we'll have a size, right? So what do we need to do? It's going to be a triply nested for loop. Let's see. All right. So for int I equals 0, I is less than size I plus plus for parting gift for tonight. Well, hey, thanks for the Franker Z. I appreciate it. First place on the bits donation. Listen, that's your golden spot, man. It's reserved now. All right, int j equals 0. J is less than size j plus plus. Now you'll notice that this is pretty boring doing this, and it's very repetitive, and it's mainly because since we're doing square matrices, we don't need to do any. There's not much thinking you have to do when you work with square matrices, because everything is of the same dimension, size in this case, so 1024 in this case. So it's not particularly difficult to solve this. So int k, and we'll just use I, j, and k. It's just simple in this case. Oops. All right, so now we need to start actually thinking. So we're also going to need I might just look up. So we need an int. We need a partial sum is equal to 0. Let's see. Actually, I don't think we need a partial sum. Why did we need a partial sum last time? Because we're iterating over every single one of the elements. But if we already have the product matrix, we don't need it because we can just add as we go along. So we'll just do plus equals. So what do we need to do? We need to index into our product matrix first. So that will be our product matrix. And that's going to be so it'll be of I and j, because we're doing I and j is our row and column, and then we need to iterate over every element of our row and column. So that will be I times size plus j. Okay, and then this is going to be, then we need ik and kj, right? So we need, so we'll do plus equals. So plus equals will be the, so let's do from the in matrix, we're going to need I times size plus k, and then we'll need k times size, right? So n of k times size plus, what is it, plus j? Yeah, plus j. I think that's it. As long as we pass in the correct matrix. And so let's just make sure that this is right. So let's just run through. So for a specific row and a specific column, we'll iterate over, and for this specific row, we'll iterate over every element of that row, multiply it by this column, which will be, or all of these columns, so k times size, and then plus j, which is the offset within that. And then that should do it. And we're already storing it in P, and we're passing in a pointer, so we'll already have the value. So yeah, so this is sequential matrix multiplication. Let's make sure I didn't do any dumb syntax stuff. I usually don't. I'm usually pretty good, except for earlier. Okay, no dumb syntax stuff. All right. So what can we do? So we'll need another P. So we'll need, we'll have a host pointer sequential, right? And we'll allocate that. So that means we'll need another one here. That way we have two results. So we're not going to be changing MNP or MN or size, so we can just write that. So we can just call matrix mul, I think we called it sequential, and then we can call that with HM, H, N, HP sequential, oops, and then N, which is the number of elements. Right, that's what we did. Yep, okay. All right, that worked. Then we can make sure that we didn't introduce some seg fault. I don't know how long it's going to take doing it sequentially. Sequential is going to be pretty slow. Okay, it didn't take too. Let's. NVProf doesn't give you the. NVProf doesn't give you the CPU time, does it? I don't know. I think it just gives you the GPU time. I could always just use gprof. Yeah, it's just going to give me that time. Okay. So now we can at least check to make sure we did it correctly. We can always just cheat a little bit too, right? Let's just print out the first let's just print out the first let's do a quick sanity check before we write the quick loop to verify it. And so let's just do P of 0 and then, or sorry, HP. And let's do H P sequential of 0 just as a sanity check. I really hate this red highlighting. I need to figure out how to get rid of it. Yeah. Oops, that's not what I wanted to do. I wanted to do NVCC, or Nvidia compiler. And let's just run this without the profiler. The profiler can take a while. It introduces some overhead because it has to inject and do a little bit of profiling like that. All right, so promising start. We got the exact same number for the first element. So it's a good little dumb, I don't want to spend too much time on this test. So we can just write a quick loop. So we can just do for int I equals 0, I less than n I plus plus, and then for int j equals 0, j is less than n, j, type correctly, plus plus. And what do we need to do? We need to do if HP of n times I plus j is not equal to HP sequential of n times I plus j. If that's not true, we will print out error. And then we will break, and we'll exit the program. So let's make sure to free everything before I forget. So we'll do this, and we'll free our HM, HN, P, and our HP sequential. And then we'll do the same thing. So we'll do CUDA free on all three things. So this will just be, oops, there we go. Our device M, our device N, and our device P. All right. All right, that worked. Okay, that should be good. Yep. So it should take a little bit longer because it has to verify everything. So, and there we go. We didn't get an error message, so we did it correctly. Okay. So that's going to be it from us today. We did matrix multiplication, and we did a sequential version of it too. All right. You have any questions? All right. So for all your CUDA knowledge, there's a lot of great resources out there. You can just Google them. Nvidia has a lot of good stuff on CUDA programming. One of the most common books people use for CUDA programming is this one, Programming Massively Parallel Processors. It says massively parallel processors, but what it really means is using CUDA on Nvidia GPUs. So that's going to be it from me, though, today. Hopefully you guys had a pretty good time. I had a pretty good time today. I'll be back again tomorrow, same time, 5 p.m. Eastern. I'll update below. I've got a YouTube channel. I'll be uploading all these VODs to there as well. Let's see. Is there anything else before I leave? Yeah, so tomorrow we'll likely do an optimized version of matrix multiplication. So we'll do a matrix multiplication version using shared memory and cache tiling. ArcStats, hey, good night, buddy. It was nice seeing you today. But yeah, so we'll do an optimized version of matrix multiplication tomorrow, and then we'll probably start getting into other more advanced things that CUDA can do. So things like CUDA dynamic parallelism, Sorry, I was getting a message. We'll do things like CUDA dynamic parallelism. We'll do CUDA streams. What else? I already said shared memory. We'll probably also do some interesting CUDA stuff, like doing some more practical applications with CUDA. So not saying the matrix multiplication isn't practical. That's the basis for a lot of machine learning. But we'll do some more machine learning specific things. So how to write a simple convolutional neural network. That shouldn't be too terrible. And we'll see what we can do with that. We might even do a couple fun projects like, oh, let's do something that will blur or de-blur an image. Or blurring's pretty easy. We'll probably just do blurring. We'll do something to take a color image and turn it grayscale. That's pretty easy because you basically just read in pixels and then you end up just scaling the values. Fourier Transforms, yeah, we can do Fourier Transforms as well. There's actually an entire library that Nvidia has dedicated to it. It's called CUFFT, so CUDA Fast Fourier Transform. So yeah, we'll do that as well. But like I said, it was nice seeing you guys today. If you enjoyed the stuff or want specific content dealing with like GPU programming, just shoot me a message. I'm pretty flexible on this stuff. I'm just kind of shooting from the hip here as far as programming or programming ideas for streaming. So I figure for GPU programming, you gotta wade in pretty slowly because it's a lot more annoying than regular CPU programming when it comes to this thread ID calculation. It's even different from what's it called, normal parallel programming, where you're explicitly thinking about threads and how they synchronize. In this case, you're doing it on such a massive scale that it becomes difficult. So intro parallel programming, you'll think of like p threads and running independent things but you'll think about running like maybe 16 things. Here we're talking about running 1024 times 1024 things, or 2 to the 20th threads at the same time. So it's not saying that one is more difficult than the other. Arguably, parallel programming not on GPUs is much more difficult than parallel programming on GPUs, especially with something like MPI. But we might do that sometime, some more distributed system type programming, or if I can set it up doing like multi-GPU programming. I don't have multiple of the same GPU though. Because I do architecture stuff, we have a lot of different architecture GPUs in the lab. So like in the machine that I'm running on right now, we're running on a Volta Titan V GPU, but there's a Pascal Titan X GPU and then some Maxwell K620. And then the machine next to me has another Maxwell Titan GPU, and there's a GTX 480 in some machine somewhere. One day I'll find where we have 4 Pascal P100 GPU someplace, and we'll use that one. But until next time, guys, have a nice evening, and I'll see you all tomorrow. Adios.